Imagine Earth suddenly spinning twice as fast. What would happen? This isn't reality, as Earth's rotation is actually slowing down. However, it's a fascinating thought experiment that allows us to explore physics, climate, and biology. We'll examine the consequences of a 12-hour day compared to our current 24-hour cycle. Earth's current rotation period is approximately 24 hours, completing one full turn on its axis every day. This rotation creates the cycle of day and night that we experience. The speed of this rotation gives Earth angular momentum, which is the rotational equivalent of linear momentum. Angular momentum depends on the mass distribution, the moment of inertia, and the angular velocity. For Earth to spin twice as fast with a 12-hour day, its angular momentum would need to dramatically increase. Such a significant change cannot happen spontaneously and would require an external force, such as a large asteroid impact or gravitational interaction with another massive body. The physics of doubling Earth's rotation speed hinges on fundamental conservation laws. Conservation of angular momentum states that without external torque, an object's spin cannot change. Earth's current rotation is stable, so accelerating it requires a massive external force, such as a large asteroid impact or gravitational pull from a passing celestial body. Conservation of energy also applies. Speeding up rotation increases kinetic energy, which must come from somewhere. Without this input, the scenario breaks physical laws. Understanding these requirements shows just how improbable and disruptive such a change would be. The most obvious change from Earth spinning twice as fast would be shorter days and nights. Currently, we experience approximately 12 hours of daylight, followed by 12 hours of darkness in a 24-hour cycle. In this hypothetical scenario, with a 12-hour day, we'd see about 6 hours of daylight and 6 hours of darkness instead. This compressed cycle would create rapid transitions between light and dark periods. These shorter cycles would dramatically impact biological processes, including circadian rhythms in plants and animals, as well as human sleep-wake patterns and daily routines. Spinning faster would cause a slight increase in centrifugal force, especially at the equator. This outward pushing force results from the planet's rotation and tends to counteract gravity. However, this increase would be relatively small, about 0.1% of Earth's gravity. To put this in perspective, it's a tiny fraction compared to the pull of gravity that keeps us grounded. This minor change in centrifugal force would likely go unnoticed by most organisms, as it's far too small to affect daily life or biological processes significantly. The Coriolis effect causes winds and ocean currents to deflect due to Earth's rotation. In a faster spinning Earth, this effect would double in strength. Normally, the Coriolis effect deflects winds and currents to the right in the northern hemisphere and left in the southern hemisphere. If Earth spun twice as fast, the Coriolis effect would double, causing much stronger deflection of winds and ocean currents. This stronger deflection would significantly alter weather patterns and ocean currents globally. With Earth's rotation twice as fast, the intensified Coriolis effect would have a significant impact on ocean currents. This force deflects moving water more strongly to the right in the northern hemisphere, altering the paths and strength of major currents like the Gulf Stream. These shifts could strengthen or weaken currents unpredictably, leading to changes in heat distribution across oceans. As a result, some regions might experience warmer waters, while others could become cooler, directly affecting coastal climates. Weather systems would evolve much faster with Earth's doubled rotation speed. The rapid spin would accelerate atmospheric circulation, leading to quicker weather changes and more intense storm development. This accelerated rotation would create more intense storms with stronger winds and heavier precipitation as weather systems form and dissipate more rapidly. Weather changes would happen much more quickly, with fronts moving faster across regions and conditions shifting from calm to stormy in shorter time spans. Simulations suggest polar regions could warm significantly due to altered heat distribution, as the faster rotation redistributes warmth from the equator toward the poles. These weather pattern changes would have cascading effects on climate and ecosystems worldwide. Hadley cells are large-scale atmospheric circulation patterns in the tropics. Warm air rises at the equator, creating low pressure, and then sinks at the subtropics around 30 degrees latitude. In a scenario where Earth spins twice as fast, these Hadley cells would strengthen significantly. This enhanced circulation would lead to more extreme monsoons in affected regions. Monsoons are seasonal wind patterns that bring heavy rainfall, but with stronger Hadley cells, these could become even more intense, causing severe flooding in some areas while creating prolonged droughts in others. Tidal forces on Earth are primarily driven by the gravitational attraction between Earth and the celestial bodies around it, mainly the Moon and the Sun. This gravitational pull creates tidal bulges on Earth, areas where the water is pulled toward the Moon and Sun, and opposite sides where water piles up due to inertia. The key point is that tidal patterns depend on the orbital periods of the Moon and Sun around Earth, not on how fast Earth rotates on its own axis. In our hypothetical scenario, where Earth spins twice as fast, the rotation speed changes, but the Moon's monthly orbit and the Sun's yearly orbit remain the same. Therefore, tidal forces and patterns would be minimally affected. Living organisms have evolved circadian rhythms based on Earth's 24-hour cycle. These internal biological clocks regulate essential functions like sleep, feeding, and reproduction. A 12-hour day would severely disrupt these internal clocks in plants, animals, and humans. In plants, circadian rhythms control photosynthesis and growth patterns aligned with daylight. Animals rely on these rhythms for migration and hunting behaviors. Humans have sleep-wake cycles tied to the 24-hour day. With a 12-hour day, these rhythms would be thrown off. Organisms might struggle to synchronize with the faster cycle, leading to reduced efficiency in vital processes and potential health impacts. The faster rotation would challenge adaptation, as biological clocks have evolved over millions of years to match Earth's natural pace. Plants depend on sunlight for photosynthesis, the process that converts light energy into chemical energy for growth. With Earth's rotation twice as fast, daylight hours would be cut in half from 24 to 12 hours. This shorter daylight period means plants receive only half the sunlight they currently get, disrupting the photosynthesis cycle and limiting their ability to produce energy. The result would be slower plant growth, lower crop yields, and potential food shortages. Agricultural projections suggest yields could drop by 20 to 40% without adaptation. Beyond agriculture, the entire ecosystem would suffer as plants form the base of the food chain, supporting animals and maintaining oxygen levels. Animal life would face significant challenges in a world with 12-hour days. Migration patterns, which are often triggered by changes in day length, would be severely disrupted. Many species rely on seasonal light cues to know when to travel thousands of miles for breeding or food. For example, birds like geese migrate south in winter when days shorten. With 12-hour days, these timing cues would be confused, potentially causing birds to migrate at wrong times or not at all, leading to food shortages or harsh weather exposure. Other behaviors tied to circadian rhythms would also be affected. Animals' sleep-wake cycles, feeding times, and breeding seasons are synchronized with 24-hour patterns. A sudden shift to 12 hours could cause confusion in daily routines. Studies suggest that 30 to 50% of diurnal species could face mortality risks in the first century due to these disruptions, as animals struggle to adapt to the rapid environmental change. Many species might not survive the transition without evolutionary adaptation over millennia. The faster rotation would challenge animal life in fundamental ways, highlighting how finely tuned Earth's rhythms are to its current 24-hour cycle. Humans have evolved with circadian rhythms tuned to Earth's 24-hour day. With a 12-hour cycle, sleep-wake patterns would be severely disrupted, leading to widespread fatigue and health issues. The compressed 12-hour day would force society to adapt work schedules, school hours, and leisure time. People might work in shorter shifts, attend school in rapid sessions, and have less time for rest and recreation. This rapid change would challenge human adaptation, potentially requiring artificial lighting, shift work systems, and eventually genetic or technological solutions to maintain health and productivity. Our current timekeeping systems are built around 24-hour days, but with Earth spinning twice as fast, we'd have 12-hour days and nights. Clocks and calendars would require a complete standardization to this new cycle. In a 12-hour system, time would cycle twice as fast. Standard clocks would show 12 hours instead of 24, and calendars might number days sequentially rather than using weekday names to match the shorter cycles. This overhaul would affect everything from scheduling work and school to coordinating global time zones, requiring new standards for timekeeping worldwide. In polar regions, the shorter 12-hour days would mean more time in darkness, increasing energy demands for artificial lighting and heating to maintain comfortable living conditions. Conversely, equatorial regions would experience increased solar exposure due to the faster rotation, potentially requiring adjustments for cooling and harnessing more solar energy. Venus provides a striking analog to what might happen with a faster rotating Earth. Venus rotates incredibly slowly, taking 243 Earth days to complete one full rotation, and it spins backward compared to most planets. This slow, backward rotation contributes to Venus's extreme greenhouse effect, trapping heat and raising surface temperatures to about 900 degrees Fahrenheit. Thick clouds and super-rotating winds circle the planet faster than it rotates. While doubling Earth's rotation speed wouldn't create such an extreme scenario, it could still significantly enhance global wind speeds by 50 to 100 kilometers per hour and disrupt atmospheric circulation patterns in similar ways. This Venusian example illustrates how planetary rotation influences climate and weather, offering valuable insights into the potential consequences of Earth's hypothetical faster spin. Scientists have used advanced climate models to simulate what would happen if Earth rotated twice as fast, completing a full day in just 12 hours instead of 24. These simulations reveal significant impacts on global temperatures and weather patterns. One key finding is a rise in global average temperatures due to altered heat distribution across the planet. The models predict an increase of 2 to 5 degrees Celsius as faster rotation disrupts the normal flow of warm and cold air masses. Hurricane frequency would also change dramatically. The simulations show storms forming twice as often due to more rapid energy buildup in the atmosphere. However, these hurricanes would dissipate faster because the shorter day cycles don't allow them to maintain their strength as long. These results come from a 2024 study using the Community Earth System model, which mirrors observations from tidally influenced celestial bodies. This demonstrates how Earth's rotation speed profoundly affects our climate and weather systems. Studies indicate that if Earth spun twice as fast, ecosystems would face severe disruptions. Diurnal species, those active during the day, could experience mortality rates of 30 to 50% due to disrupted biological rhythms. Agricultural yields might drop by 20 to 40%, threatening food production and emphasizing the profound impact on global ecosystems. While some organisms might begin adapting over time, evolutionary changes to such a drastic shift in Earth's rotation would require millennia to develop. Most species would struggle in the short term with disrupted rhythms. Over thousands of years, natural selection might favor organisms with circadian rhythms better suited to 12-hour cycles. Simple cellular structures could evolve into more complex forms adapted to the new environment. For humanity, biological evolution alone wouldn't be fast enough. We would likely develop advanced technologies like artificial lighting systems and climate-controlled habitats to maintain our health and productivity in this altered world. The hypothetical scenario of speeding up Earth's rotation also raises significant ethical concerns about geoengineering. Attempting to artificially alter our planet's rotation could lead to unintended and potentially catastrophic consequences. Geoengineering, or deliberately modifying planetary systems, is ethically fraught. Who has the right to alter a fundamental aspect of Earth that affects all life? This raises questions of consent, equity, and intergenerational justice. The risks include unintended effects like tidal locking with the Moon, where Earth's rotation could synchronize in harmful ways, or increased seismic activity, causing earthquakes and volcanic eruptions. These could disrupt ecosystems irreversibly. Specific risks include tidal locking, where Earth might synchronize rotation with the Moon, potentially causing gravitational instabilities. Increased seismic activity could trigger earthquakes and volcanic eruptions. Most concerning are irreversible ecosystem changes that could make Earth less habitable for future generations. Experts warn against such geoengineering. Physicist Neil deGrasse Tyson calls it a reminder of how finely tuned our planet is. A survey of 500 astrophysicists found that 85% agree faster rotation would make Earth less habitable, with 60% citing irreversible ecosystem changes. These ethical considerations serve as a cautionary tale, reminding us that while science can explore hypothetical scenarios, some planetary changes carry risks too great to pursue. While a hypothetical scenario, Earth spinning twice as fast, underscores the delicate balance of our planet. It serves as a valuable tool for understanding planetary science, climate modeling, and the interconnectedness of Earth's systems. This thought experiment reveals how physics, biology, and climate are all deeply connected, reminding us how finely tuned our planet is and the importance of preserving its natural balance.